Morning.
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 Morning. Let's see.
Morning.
Can probably get started soon since it's already 10:30. Yeah, please turn on your video to give the course a more personal feeling or a more human feeling. Otherwise, you feel like that you're in the robot class or something. Okay, let's see how we can do this better. Let me share my screen. Okay, today I'm going to talk about reflection, transmission, and interesting physical phenomena. Okay, some of these might have been covered in your undergraduate course if you've had a undergraduate course in electromagnetics, and some of you might not have this background. So this will be like a revision for many of you, but new stuff for some of you. So this is a wonderful stuff because we are going to obtain closed form solutions from full-fledged Maxwell's equations. We started out with Maxwell's equations in 3 dimensions, and then we simplified Maxwell's equations into transmission line equations or telegrapher's equation. And things are a lot simpler there, but now we're going to solve Maxwell's equations in their full glory. Okay, so we begin by solving the reflection and transmission from a single interface problem. So the problem that we're going to discuss will look something like that. And we assume that we only have a single interface between 2 media, medium 1 and medium 2. Okay, and that we have solutions to Maxwell's equations in region 1 or medium 1. And then we have solutions to Maxwell's equation in region 2. And we will use physical insight to guess how the solutions would look like in these 2 regions. And then we mesh boundary conditions to obtain the unknown coefficients. Okay, so let's begin by starting the derivation. And we like to guess the solution in region 1 consisting of plane waves. Plane waves propagating in this manner in region 1. And then a reflected plane wave that will propagate in this manner with a k vector or the beta vector pointing in that direction. And then a transmitted wave in region 2 propagating in this direction. So we assume the TE case for simplicity. The TE case is also called the perpendicular polarization. Because in this case, the electric field, as you see from the picture on the left, is pointing out of the paper. And hence it is perpendicular to the paper, and it's called a perpendicular polarized wave. And sometimes it's also called a TE to Z wave. Okay. It is actually with respect to the Z axis that this electric field is transverse. Because in a homogeneous medium free space, you can just say TE and it's well understood. But in the case where you have an interface, you have to sometimes specify that it is TE to Z. So we can write down the solution in region 1. Okay, the solution in region 1 for the incident wave would be something like a Y polarized wave. The electric field is polarized in the Y direction out of the paper, and then it has a certain amplitude, and then it propagates like a plane wave. And in order to make it propagate like a plane wave, we put in this phase factor that you have learned in lecture 7, for instance. Okay, and if you write out beta I, okay, beta I would be something that points in that direction that you have seen is has a positive x component and a positive z component. Beta I would be something like a vector with positive x component plus a vector with positive z component. Okay, that's how your beta I would look like. And if you substitute that in, you will get the fact that the wave field written in greater detail, if we do the dot product and the exponent, and then I will get z. Okay, if I plug in the proper components, I get this to be my field in region 1 for the incident wave. And then in region 1, I have a reflected wave as well. And that reflected wave is with a beta vector that propagates in that direction. So beta R would have a positive x component, but it will have a negative x component, as you can see from the picture. Okay, it has a negative x component, a negative z component. So when they write down the z, must well just put down the sign and call that to be that. Okay, and then when you write this down, the reflected wave will have an unknown amplitude, and we do not know what the amplitude is. Let's call it RTE. So this unknown amplitude we call E naught times RTE. Okay. Okay, so that is the unknown amplitude. And then when we write things out in gory detail, we will have to put in this thing, and then the beta R vector dot with R. This will represent the wave that is propagating in the desired direction that we show on this transparency on this slide over here. And then we can also write down ET, the wave in the transmitted region. It will still be white polarized, but then with an amplitude multiplied by TTE. Okay, and then it will have a beta vector of beta T, and you can write down beta T. Beta T would very much be like beta I, pointing in the same direction. Okay, pointing in the same direction with positive z component and positive x component. And then if you put these things out, it looks pretty complicated, a lot more complicated than transmission line theory. But we have two unknowns here. The unknowns are RTE and TTE. Okay, so what do you think we should do next to find these two unknowns? We will have to mesh boundary conditions. We have the electric field equations. We can mesh boundary conditions for the electric field. And what would the boundary condition for electric field at this interface in terms of boundary conditions? Does anybody know, or does somebody want to turn on your mic and tell me what the boundary condition should be at the z equals 0 interface, which is this point over here? What should be the boundary condition there that we should impose?
The tangential part of the electric field should be continuous.
Wonderful, yes. Tangential part of the electric field should be continuous, and the tangential component of the electric field is a y component. If you think about y component, it is parallel to the surface, and hence these are all tangential components, and you can impose them to be continuous. Okay, and you can get that quite easily. You can put them down. You can make sure that this thing plus this thing, which is a total field in region 1, should be equal to that. Okay, so you can immediately see that the boundary condition should be 1 times this factor. Okay, let me write down this factor. I'm going to write down this factor explicitly, setting z equal to 0. Okay, so if I write down the factor, it would be e to the j beta ix x. But because I set z equal to 0, the exponent to the z just becomes 1. And then I have to add in the reflected wave. Okay, I do the same thing to what I have in the exponent there. And again, because of the fact that I set z equal to 0, this component disappears. So if I add the first two waves, EI and ER, and then set z equal to 0, I get this to be the tangential component of the electric field in medium 1. And then in medium 2, I would have to write that down. I would do the same thing. E naught is common to all the three expressions, so I don't have to write E naught down. And then I would write down the thing in the exponent now. Now I'm going to set z equal to 0, so this term will disappear. Okay. And I need this equation to be satisfied. Okay, I need this equation to be satisfied, but apparently this is not enough to enable the solutions of the Maxwell's equation for this problem. So we need something else. We need something in addition to what we have seen. And then we need the magnetic field. Okay, so we will derive the magnetic field next. In order to do that, we have to go to Maxwell's equations and use Faraday's law. Curl of E is equal to j omega mu h with a minus sign. I better not forget my minus sign, because we often have to hop between the optics community and the engineering community. In the optics community, the time convention is this. In the engineering community, the time convention is this. So you have to make sure that you have to learn how to switch between minus I and j. Okay, so in order to simplify this equation, we are only dealing with plane waves, so we can make the assumption that the del operator, because we are only working with plane wave, becomes j beta. Okay, and Maxwell's equations just becomes j beta cross E for the left-hand side is equal to minus j omega mu h on the right-hand side. That is what becomes of Maxwell's equations or Faraday's law. And then now I can work on all the components of the magnetic field. I can work on my HI first. So you see how tedious this is when you work with full-fledged Maxwell's equations. And if you work on this term, you will get that this should be beta I cross EI over omega mu 1, because I'm dealing with region 1. Okay. And you can go through the details, which I don't feel like doing. I can do it if you want me to. I can actually go through the detail of doing this vector algebra. Okay, let me just work out the detail of this. And this would actually be something like beta I cross y hat E naught e to the minus j beta I dot r over omega mu 1. Okay, and if you go to the vector algebra, you can show that if you take the cross product properly, you don't have to use a determinant to do this cross product. Many students, when they come to having to take a cross product, they will write down the determinant rule. And instead, I would suggest that you just use the very simple rules that you know for x cross y is equal to z hat, y cross z equals x hat, and then z cross x is equal to y hat. And then the rest of the cross products are 0. Okay, we just use this very simple rule. You can use the distributive property of cross products and do it term by term, and then you will obtain the fact that this is actually just equal to z hat beta ix minus x hat beta iz over omega mu1. Let me write my omega mu1 properly. E naught e to the minus j beta I dot r. Okay, this would be what I have for hi, and you can get the hang of it, and you can see how complicated it is. Okay, so I will not do the other components, but you get the hang of it. You know what I'm talking about when you have to do this in gory detail. You just have to do this very carefully, so you can actually go and work out your reflected field HR. Okay, HR will be given by beta r cross ER over omega mu1, and then you can do the work yourself at home, and then you can go and look for HT, which would be beta T cross ET dot omega mu2. Remember, I have to replace mu1 with mu2 because I'm in region 2. Okay. So, so we have this additional magnetic field, and we will have to mesh the second boundary condition. The second boundary condition is naturally following from Ampere's law, which says that tangential H field has to be continuous. The first boundary condition we had followed from Faraday's law. Okay, so if we put in the second boundary condition, what we would have is that we have to add the components of the field, magnetic field on the region 1, and then components of the magnetic field in region 2 in mesh boundary condition, and you will get the fact that you will have something that looks like this, that the incident magnetic field in region 1, if you work out the detail, I work out the detail for one case over here, okay? The tangential component will be just the x component. The z component is not tangential, so I can just ignore that. So if I write down the tangential component for region 1 for the incident field, and then set z equal to 0. And then divided by omega mu1, that is the hix for the incident field, and then you would have that for the reflected field, there's a sign change. You have to be very careful about this because the beta z would change sign. Okay, because for the reflected field, the beta points outward. So the beta z has a different component in sign compared to the z component in this spectrum. So there's a sign change, and you have to be careful about this. If you don't take care of this sign change, you will not get the correct answer. So if I write out the other details, it will look something like this. And then I will have to put the reflection coefficient for the reflected field, and then I will have e to the beta ixx. Okay, and then I will have to mesh this to the tangential component of ht. Okay, if you write down carefully that thing, you get beta tz over omega mu2 now. Sorry, this is mu2. Okay, you get mu2. And then tte, e to the minus j beta t xx. Okay. by setting z equal to 0. You have to set z equal to 0 to mesh the components. So this is just the reflected field. And then this is the, actually this is the x component of the incident field. This is the x component of the reflected field. This is the x component of the transmitted field. Okay. So there are two equations and two unknowns now. The first equation that we obtained was this one over here. The second equation that we have now would be this equation over here. So we have two equations and two unknowns. I forgot to put in a E naught here. Okay, there should be an E naught somewhere. Okay, the E naught cancels out, so it doesn't matter. Furthermore, we are going to say one more thing. We say that if you look at these equations, the first equations that we have, okay, over here, equations 1, maybe I should call this equation 1, since it's important, okay? And it has to be satisfied for all x, okay? It has to be satisfied for all x. And the only way that this equation can be satisfied for all x is for these betas to be the same. Can you see that? So unless the betas are the same, they cannot be satisfied for all x, okay? Second equation, the same thing holds. I need this equation to be satisfied for all x. The beta must be the same. So I immediately conclude that by eyeballing the equation, beta ix must be equal to beta rx must be equal to beta tx. Okay, this is called phase matching. Okay, otherwise the boundary condition cannot be satisfied. Physicists like to call this momentum matching, because momentum is the same as phase to them. The beta vector is also called the momentum vector. Okay, so we have this condition, and from that actually you can learn a lot of things. You can get Snell's law out of this thing. We'll discuss a bit about that later on, because I will talk about Snell's law later. Okay, but then it also allows you to cancel these terms out, because all these are the same expressions now. Okay, and then I can cancel the E naught because they're just common to all of them. And then I can almost cancel the omegas out, not the mu's though. Okay, so if you look at your equations that you have now, the first equation, you can also cancel the phase out because they are now the same phase. Okay, and then what you have is actually two simplified equations. The first equation gives you from the previous slide over here, 1 plus RTE is equal to TTE. Okay, that's from equation 1. Equation 2, which is the second important equation, if you do things correctly, you get beta IZ over mu 1 minus RTE is equal to beta TZ over mu 2 TTE. I forgot to mention one thing though. I have switched this to beta IZ. Actually, I did it wrongly. To be kosher, I have to keep this to be beta R. That means if to do the thing carefully, if I cross my T's and dot my I's carefully, then the second term should actually have beta R. Okay, beta R, which means that this term here should be beta R. Okay, and this term here should be beta Rx. If I had been careful about what I did, okay, I was not too careful. So I just wrote them as beta Ix. But we know that these are plane wave solutions in two different regions. Because they're plane wave solutions, it has to be true that beta Ix squared plus beta Z squared is beta 1 squared. And that is also true for the reflected plane wave. So beta Rx squared plus beta Rz squared must also be equal to the same constant. Okay. And then in region 2, I have a different relationship. These are called the dispersion relationship for plane wave. Since in region 2, I will have a different relationship, then I will have beta Tx squared plus beta Tz squared is equal to beta 2 squared. Okay, but if you eyeball these two equations, okay, we already argued that by phase matching, these two are the same as each other. Okay, these two are the same as each other by phase matching. Then the only way that these two equations can be satisfied is that beta Iz has to be equal to beta Rc. Okay, but here I cannot claim that. Even though I can say that beta Tx is the same as beta Rx, I cannot claim that beta Tz is the same as beta Iz. So I have to keep this distinction here, but I can make this beta Rz to be beta Iz and take it outside the factor. Then I have two equations and two unknowns that can be easily solved with the notion that beta Tz is not the same as beta Iz. Okay, so two equations, two unknowns. It will be straightforward algebra. You can solve them. I'm not going to go into the detail of solving them, but I just tell you the results. Okay, RTE after solving them would be something like beta 1z over mu1 minus beta 2z over mu2 divided by beta 1z over mu1 plus beta 2z over mu2. Okay, so these are reminiscent of what you learned in transmission line theory, that you have a reflection coefficient gamma, and that gamma you find it to be Zn minus 1 over Zn plus 1. So it's like difference of two numbers divided by the sum of two numbers. You can always rewrite them so that they look like the transmission line equations. Okay, and over there you can also write this as Zl minus Z0 over Zl plus Z0, which is also the difference of two numbers divided by the sum of the two numbers. So this reflection coefficient have similar terms. Okay, then you can work out your TTE. TTE is just 1 plus RTE because you get that from this equation over here, and you can work that in your mind. It would be 2 beta 1z over mu1 divided by this common factor. Okay, in the denominator. But for good mnemonics, I would have to usually write this in terms of the regions 1 and 2. This would be the reflection coefficient between region 1 and region 2. Then in order to memorize this coefficient very easily, I would think of the first term is always related to region 1 and the second term is always related to region 2. And you just take the difference of these two numbers divided by the sum of these two numbers. You will get this reflection coefficient and transmission coefficient correctly, and these are known as Fresnel reflection coefficient. Okay, and it seems that there's another person by the name of I forgot his name, and this was known in the Islamic world around AD 900. Okay, in the Islamic world. Okay, so you can do this for TE polarization. You have all these things that are known to you, and then what happens is that you can do the other polarization, which is TM. And if I look at TM polarization, it is just the dual of the TE polarization, because if I replace E with H, which is minus E and so on, I get the second figure. Again, this figure where it is TM polarization, where the H field is perpendicular to the paper now. So the two problems are dual to each other, and we can apply duality principle, and then hence get the solution right away. Okay, we can get the solution right away by duality. Then I can actually write down the solution of this TM polarization. Let me draw a line here by duality. Okay, and you can say RTM 1, 2 is equal to beta 1z over, instead of mu1, you use epsilon 1, because you have to do the swap for media as well. Okay, you have to replace the media epsilon 1 with mu and so on. And then beta 1z over epsilon 1 plus beta 2z over epsilon 2. So this is for TM polarization. And then you can do the same for TM polarization 1, which is 1 plus R 1, 2 TM. And you have to be careful, okay, because we use duality principle. These are reflection coefficients for electric fields, because that's how we define them. We define this reflection coefficient to be that for the electric field. So when we use duality principle, this will be the reflection coefficient and transmission coefficient for magnetic fields. Okay, you have to make that distinction, because these are not reflection coefficient and transmission coefficient for electric field anymore. So I would like to mention that these are coefficients for H field. Okay, because some textbooks will report the reflection coefficient for the TM polarization for the electric field still. And you will see that these coefficients will look quite different from what I have written down here, because what I have down here is that for the magnetic field. Okay, are there any questions before we move on? Okay, if there are no questions, then I would like to see what kind of interesting physical phenomena we can get out of this. And the first one is the total internal reflection. And total internal reflection happens when the wave is totally reflected. Okay, and if I just look at R12TE, for instance, R12TE, it will be given by beta 1z over mu1 minus beta 2z over mu2 divided by the sum of this thing. And I know the dispersion relationship has to be satisfied. So in region 1, beta 1z squared plus beta 1x squared is equal to beta 1 squared. And then beta 2z squared plus beta 2x squared is equal to beta 2 squared. But because of phase matching, these two have to be equal to each other. Okay, so you only have the thing been different that way. And then you can actually see this phase matching condition using a diagram such as this one. Okay, I will put this diagram here, that you can draw a circle in the medium 2 or medium T, and then you can draw a circle for the medium 1. And these are just equations of a circle. If you look at this thing, they're just equations of circles. So if you look at x component and the z component, x component and the z component, they form a circle such as this one over here. And what it says is that if you were to change your beta x, the beta vector in region 1 would point in different directions. For instance, this is beta I, okay? And this is beta t. And those beta vectors would change depending on the medium you're in, because the right-hand side is just the length of the vector. The length of the vector is larger in medium t or medium 2, and the length of the vector is smaller in medium 1 in this case. And the beta vector has to be lying on the circles, or these two circles. And because of phase matching, the x components have to be equal to each other. So this diagram is drawn in such a way that the two beta vectors, the three beta vectors in fact, all have the same x components. And phase matching is satisfied. So this is a phase matching diagram for the K surfaces, okay? And you can see that when you see that phase matching is satisfied, but you can go to the other case where beta t actually is smaller than beta 1, okay? And this would be this diagram over here. Region 2 has a smaller beta t than the beta in region 1, and you will have to draw the circles this way. The left circle would be a bigger circle than the right circle, and then the beta vectors will still be pointing in this direction, and you can draw them, and they will come a juncture that if you increase the angle of incidence large enough, that phase matching is still satisfied, but beyond that, phase matching cannot be satisfied. Can you see in this diagram? If I make this incident angle larger and larger, phase matching would not be satisfied. And beta t would actually become parallel to the surface. So you can go back to this first diagram and say that, well, if I increase my incident angle, beta t would have to change accordingly, okay, according to Snell's law actually. You can actually get Snell's law from this picture over here. You have the fact that beta Rx is equal to beta Ix, and this means that beta 1 sine theta I is equal to beta 1 sine theta R. And this is only possible when theta I equal to theta R. This is the simple law of reflection. And if you look at this equation again, you will see that beta Tx must be equal to beta Ix. And this says that beta T or beta 2 sine theta T is equal to beta 1 sine theta 1 or sine theta I. And this is just Snell's law. Okay, this is just Snell's law. Okay, and this is just what we call the law of reflection. Incident angle has to be equal to reflected angle. That's something you learned in high school. And this is Snell's law due to phase matching. And you can see it from this diagram over here. But you can see that when you make the incident angle bigger and bigger, this transmitted angle will be bigger and bigger. But for this diagram, there's no problem. But for this diagram over here, it will come a juncture that this phase matching cannot be kept anymore. And this transmitted T has to become an imaginary vector. Okay, it's hard to draw an imaginary vector, so we won't draw that here. But what I'm trying to get at is that there is a juncture where you have this beta 2z, okay, beta 2z becomes pure imaginary, okay, beta 2z beta 2z, as you can see, is beta 2 square minus beta 2x square, which is beta 2 square minus beta x square, because the betas are the same all regions due to phase matching. And that you can see that it will come a juncture where beta 2 square is beta, I can call this beta 1 sine theta square. If beta 1 is smaller than beta 2, it will come a juncture that this cannot be satisfied anymore. Did I say it right? It is a case where beta 2 is smaller than beta 1. Again, when beta 2 is smaller than beta 1, it will come a juncture when you increase this angle of incident. This is angle of incident. That this one will become a negative number. And when that happens, then beta 2z becomes a pure imaginary number. Let's call it minus j alpha 2z. Okay, it becomes a pure imaginary number. And when that happens, what you have is that you have the fact that one of these numbers, this will become pure imaginary. This becomes pure imaginary. Then R12TE is of the form of A minus JB over A plus JB. And if you have a number like this, if your math is very good, you immediately see that these two numbers are complex conjugates of each other. And if you were to take its magnitude, it will be the magnitude of the denominator over the magnitude of the numerator. Did I say it right? Maybe not. It's the magnitude of the numerator over the magnitude of the denominator. And these are complex conjugates of each other, so they have the same magnitude. And they will always have the magnitude of 1. Okay. But they will have a phase. Okay. You can find the R12TE would always have a magnitude of 1, but with a phase that you can actually work out quite easily using polar method, polar mathematics, and the phase will be given by this. Okay. And that this is interesting. The magnitude is not changed. The reflected wave always have the same magnitude as incident wave. This is called total internal reflection, which I've written up there. Okay. But the phase would acquire a phase shift. So if you have this happening to you, the wave comes in, everything is totally reflected, but there is a phase shift for the wave. Okay, it comes in 1, but it gets reflected. And what happens is that in region 2, the beta 2z becomes pure imaginary, which means that the wave is evanescent in region 2. Because beta 2z becomes pure imaginary. So when that happens, you have evanescent wave in region 2, a totally reflected wave in region 1. Furthermore, there is a phase shift associated with that reflected wave. Okay, there's a phase shift associated with that reflected wave. And it's not easy to understand this at this point, perhaps for you, but a phase shift in the frequency domain is equivalent to a time delay in the time domain. So if you were to study this in the time domain, what the physical meaning of this phase shift is, and if you do some time domain simulation, and if you imagine a pulse traveling into this interface, because of the total internal reflection, there'll be a time delay for the wave before it gets reflected. Okay, the wave will come in here, but it will hobble around at this interface for a little bit before it gets reflected. Okay, that is called the Goose-Henson shift. And you can actually simulate this on the computer if you have the numerical software to do that. Okay, this is quite an interesting phenomenon. So this total internal reflection is very important. The most important physics is that you see a Goose-Henson shift. Everything is totally reflected. But you can use this to build technologies. in the sense that if you have two interfaces, two optical thin films, or this is called an optical thin film. Let me write it down. And if you choose the material properly, so that total internal reflections occur at the top interface as well as the bottom interface, the plane wave will bounce just back and forth. And the plane wave will have its energy trapped inside the thin film with no loss of energy, because what you have is exponential decay and exponential decay. You can show that an evanescent wave, okay, does not carry power. It carries only imaginary power. Because it carries imaginary power, it actually cannot carry energy away from the waveguide, and then the energy of the waveguide will be completely trapped. You can show as the homework exercise that you can take all these complicated expressions that you have derived in region 1, okay, and then you take the E field that you have derived there as well as the H field that you have derived there, and you can actually do some simple exercises to find E cross H, okay? You can find E cross H. So it's a lot of cranking, but you have the ability to do it now because you can find E in the upper region, and then you can find H in the upper region. And when you have a evanescent wave in the upper region, you will find that the power is purely imaginary, which means that it can only carry reactive power. You can sort of see it here if you look at the H field. So if you have a transmitted wave which is evanescent, this becomes an imaginary number. And if you cross this with the electric field has no beta. If you look at the electric field in region 2, there's no beta associated with that. So E cross H will give you something that is purely imaginary. And you find that the power is in fact complex and purely reactive. We call this the reactive power. And you have learned about reactive power from transmission line theory and circuit theory before. Okay. You can also use this kind of thing in an optical fiber. You have to recall now that the physics of evanescent waves comes only from phase matching. So if you have this optical fiber, the wave that travels in the z direction has to be something like this. In the radial direction, it will be very complicated. It's beyond your knowledge to understand how the wave travels radially, but it will be in terms of Bessel functions, very difficult things, okay, that you will learn later on in the course. But in the z direction, okay, it travels like a plane wave, a traveling wave in the z direction. And again, due to phase matching, all the waves in all the different region, the cladding, the core, and the air, all have to have the same kind of dependence for phase matching to occur. Because of that, they have different dispersion relationship. In the cladding, you might have beta z squared plus beta c squared is equal to, let me see, there should be R. Okay, the radial wave number is beta c squared. And then in the air, you have beta z squared plus beta a squared. Let me call beta 0 for air. It's equal to beta, sorry, I should call this R for air. And then beta 0 squared. And in the core region, you will be beta z squared plus beta core square is equal to beta. Let me see. This is cladding. Yeah, this is no good. I'm using core and cladding, so I will call this core, and this is cladding. Okay, this is cladding. This is air. You can see that all the betas have to be the same, and the same principle applies, that when you are beyond the critical angle, one of the wave numbers have to be pure imaginary, and the wave has to be completely trapped inside the optical fiber. Okay, I'll stop here. Are there any questions before we stop? Okay, does anybody have any questions regarding this? This is a very important topic. It's kind of tedious to have to do all the vector algebras correctly, but this is the price you have to pay when you want to find the solutions to Maxwell's equations in their full glory. Okay, but it offers you physical insight, and you can use your understanding of wave reflection and transmission in simple transmission line theory to understand the theory of this more complicated geometry and so on. Okay, I'll let you go unless you have any questions. Does anybody have any question? If not, then I'll let you go then. Enjoy yourself and take care and be safe out there. We still are not completely free from the coronavirus yet. You take good care of yourself. Okay. Bye-bye.